So just like Copernicus changed how we saw the solar system, there's another big shift happening in our view of the universe. It's causing a stir called the crisis in cosmology. Basically, our estimates and understanding of things like the universe's age, size, and how fast it's growing are way off. Neil deGrasse Tyson says the James Webb Space Telescope, JWST, kind of paused this debate with a picture that messes with what we think we know about materials. What's this crisis, and how does the JWST fit in? Well, it's not really causing the crisis. Think of it more like a survey that's been going on. The crisis is that our interpretation of the universe is being questioned, especially its age and size, which are pretty uncertain. The JWST is a big deal because before, we couldn't see very far into the early universe. Now, with its advanced tech, astronomers can check out really distant objects, giving us new info and testing our old ideas. It's like looking back in time, closer to the Big Bang, watching galaxies form when they were young and getting data that might confirm or deny what we thought we knew. To understand the crisis, we need to understand the current picture. The main model, called the Hot Inflationary Big Bang Model or Lambda CDM, has been good at explaining things like gravitational lensing, the cosmic web, and how galaxies have changed. The Lambda CDM model says the universe started with a Big Bang, then expanded super fast, and keeps expanding. It includes dark matter, which pulls things together with gravity, and dark energy, which makes the universe expand faster. But new observations, especially from the JWST, might mean our model is wrong or needs tweaking. The Lambda CDM model makes predictions about galaxies at different times in the universe's history. For example, it says that galaxies far away in the past should be smaller, less developed, and have fewer heavy elements than the ones we see nearby. That's because heavy elements are made in stars and spread out by supernovas, which takes time. According to the model, galaxies should be smaller, bluer, less evolved, and have fewer heavy elements when we look far away, which would mean there was a time without any stars or galaxies. But scientists have found stuff that doesn't fit, which is why there's a crisis. The crisis is all about not knowing exactly how old the universe is. Different ways of figuring it out give different answers, and cosmologists are struggling to make sense of it all. One way to find the age is to study cosmic background radiation, which tells us about the universe's expansion. We use math models like the Friedmann equations, based on Einstein's theory, to figure out how fast it expanded at different times. The CMB, cosmic microwave background, leftover radiation from the early universe, is key. Maps of the CMB, like the ones from the European Space Agency's Planck mission, give us a lot of info, but they don't have good data on dark energy. Still, scientists can use the Friedmann equations and other observations to estimate the universe's expansion rate and age. Another way to find the age is to watch exploding stars, specifically type Ia supernovas. These supernovas are like standard candles because we know how bright they should be. By comparing their actual brightness to how bright they look, we can figure out how far away they are and how fast the universe was expanding at different times. This method helped us discover dark energy in the 1990s, which is now important for cosmological calculations. It's helpful for finding the Hubble constant, which measures the universe's expansion rate. NASA says that the expansion rate is important. If the expansion is slowing, it might mean there's some unknown force, maybe dark matter, affecting it. If it's speeding up, it could mean dark energy is causing the universe to grow. In 2018, scientists found that the universe's expansion rate seemed different depending on where they looked. The Hubble Space Telescope showed a faster expansion nearby, while the Planck telescope showed a slower expansion farther away. This shows how big the universe is and reminds us of Edwin Hubble, who first suggested the universe was expanding in 1929. Hubble saw that distant galaxies were moving away from us, which confirmed the expansion. If we looked at the universe's expansion without focusing on any specific area, we'd see the same speed everywhere. Early calculations were based on limited data, but with better tech like the Hubble and Gaia telescopes, we've gotten better measurements. Different telescopes use CMB readings to calculate the Hubble constant, but this is hard because there aren't many supernovas to see far away, which limits what we can see of the universe. Since we found dark energy in the 20th century, scientists have been confused by the differences between these ways of finding the universe's age and expansion rate. As our measurement tech gets better, we see smaller differences, which leads to the development of more advanced systems. Although it raises more questions than it answers, the differences are small, only 10 to 20 million years apart. But since the universe is around 13.77 billion years old, it's something we need to look at closely. One reason could be that we're making mistakes when we measure the CMB, even though it's one of the most accurate measurements we have. Another idea is that we don't fully understand dark matter and that it might change over time and be connected to dark energy or something else we don't know about. This has led to experiments. Also, the supernova measurements might not be accurate because star explosions are complicated, which can mess up our models. If we can fix these models, it might clear up the differences. The JWST's discoveries have made this crisis even worse. Tyson says the JWST has found things in the universe that we can't explain with our current understanding. This means we need to update our science knowledge, but we don't know where to start. To understand how big this is, let's look at the universes beginning about 50 million years after the Big Bang. Stars, black holes, and star clusters started to form. Maybe as soon as 50 to 100 million years later, but these things should have been rare. We don't know how common galaxies were at later times, between 400 million years after the Big Bang. The JWST is showing us galaxies that are much farther away and older than what our current model predicts. This means our model might need a major update. The discovery that galaxies were important to the expanding universe is big. The JWST pictures show galaxies that formed much earlier than we thought, causing this crisis. This has to do with galaxies and redshift, which is a standard measurement in cosmology. According to the model, hydrogen started to appear 400,000 years after the Big Bang when protons and electrons joined, leading to hydrogen recombination. This turned the universe into a soup of hydrogen atoms with some helium and leftover radiation. Gravity from the radiation then pulled small changes in this hydrogen gas together to form the first stars. These early stars, mostly made of helium and hydrogen, fused elements, making heavier elements like carbon and nitrogen. These elements helped galaxies form by absorbing heat and emitting cooling photons, which helped gas condense into galaxies. How galaxies form and evolve is complicated. At first, gas was mostly hydrogen, but over time it got mixed with heavier elements made in stars. So galaxies formed not just from hydrogen and helium, but also from carbon, oxygen, nitrogen, and other things needed for life. Studying how galaxies form and change helps us understand the bigger picture of the universe. It shows us how galaxies interact, grow, and change, and how they contribute to the overall structure. The JWST, with its ability to study distant galaxies, has shown us a lot about these things, including the formation of the first galaxies and stars. One of the most exciting things is that the JWST has found galaxies that formed much earlier than we thought. Some of these formed only a few 100 million years after the Big Bang, which goes against our current models. This means we might need to change our understanding of the universe's timeline. These galaxies, more mature than expected so early on, give us new ideas about how the universe went from a hot, dense state after the Big Bang to the more structured cosmos we see now. The JWST's observations also give us data on the first stars. These stars, mostly hydrogen and helium, started to fuse elements, making heavier elements like carbon, nitrogen, and oxygen. These elements were key for later, more complicated things like planets and life. The JWST lets us study these processes in detail, showing us the conditions when the first stars and galaxies formed. Besides galaxies and stars, the JWST has given us insights into how dark matter is spread out, which is still a mystery. Dark matter doesn't emit, absorb, or reflect light. So we can't see it with most telescopes, but we can see its gravity. And the JWST has found how dark matter affects how galaxies form and move. By studying how visible matter and dark matter interact, we can better understand how dark matter shapes the universe. Dark energy is also important, and the JWST has helped with that too. We think dark energy makes the universe expand faster, but we don't know what it is. We can see its effects on the large-scale structure of the universe. The JWST's observations of distant galaxies and the cosmic web have given us new data that might help us figure out dark energy, possibly giving us clues about the universe's future. The crisis in cosmology is reshaping our understanding of the universe. And as we gather more precise data, it's becoming clear that the story we've been telling about the cosmos might need significant revisions.